And he said, "Oh, they're called tapping sticks." He's a very clever man. So in my language, we call this yidiki. Yidiki. And the word yidiki means voice. These are called bilma. Bilma. Not just any wood either. It's got to be certain wood that we use. How we play yidiki is breathe in through the nose, blow out the mouth at the same time. It's what they call circular breathing. When we make animal noises, we use our voice, and how we make our songs is we sing. There are words that we say, like didgeridoo, didgeridoo, didgeridoo. If I change that song, and if I sing wackadoo, wackada, wackadoo, wackada, wackadoo, wackada, then the song will sound like this. Wackadoo, wackada, wackadoo, wackada. So lots of things have a song. I haven't got time to go through that repertoire this morning, but just to show you how good I really am on the yidiki, I'm going to tell you a story. This story is about a hitchhiker. So this man, he's run out of petrol in the middle of the desert, and he's hitchhiking his way back to town. 3 cars will go past, and he keeps walking. In the distance, you'll hear a truck. The truck will slow down and stop. You'll hear the truck driver say to the hitchhiker, "Where are you going?" And the hitchhiker says, "Oh, up the road." And the truck driver says, "Okay, mate, get in." He gets in the truck, he shuts the door, the gears on the truck will change, and the truck driver will finish off the story by blowing on the horn. And that's the story of the hitchhiker. Pretty good, eh? All this is a hollow log. It's a hollow log, nothing inside. We don't actually hollow it out. The termites eat all the wood in the middle, and we just tap on it to see how far along they've eaten. Then we cut it down, take the bark off it, paint it, and that's yidaki. The most important thing we've got to do when we make yidaki is make sure there's no more termites inside before we play. And I'd just like to finish off now by also playing a welcome song on the yidaki. Yidaki does not come from New South Wales. It's not a traditional instrument down here. It's a borrowed instrument. It only comes from the top parts of Australia. So I'd just like to finish off by playing a welcome song on the yidaki. Once again, thank you and welcome.
Hello, everyone. Good morning. Thank you very much for coming to the third day of our federated conference. Before I start introducing the keynote speaker, I do have a message from HPCA. We have the ACM computer architecture blog that has been sending me messages about selecting folks who are attending this conference who are interested in submitting their interesting experience, reports, or journey to write a blog with them. If you're interested in that, please contact me or contact our web chair. So we'll and then we'll select a number of those Journey to Sydney for HPCA blogs that will be selected and for that article. Yeah, thank you. Okay, so it's my great pleasure to introduce our keynote speaker. So in the past couple of days, we have been here discuss topics of compiler programming language for high-performance computing, and today we finally get a chance to, it's a great honor for me to introduce someone who has dedicated his career in computer architecture. So I want to introduce you Sudhava Gurumurthy, and he is a fellow at AMD. He has done, for many years, he has done great work for computer architecture, especially reliability and serviceability. He's responsible for research and development in these areas at AMD. His work has impacted AMD products as well as the industry in general. Before AMD, he was an associate professor at University of Virginia. He has won a range of impressive awards, including NSF Career Award, Google Research Award, as well as being part of the ISCA Hall of Fame. He's also currently served in editor-in-chief for IEEE Computer Architecture Letters. And today he's going to talk about his work on computer architecture reliability. Welcome. Thank you. Take this stage.
Thank you. Thank you, Shuaiwen. And it's a pleasure for me to be here. So I just want to apologize in advance. I need to give this keynote seated, just I'm dealing with something. So with that, what I want to do today is, as the title says, Resilient System Research to Practice, is to walk through a couple of examples, set some principles, and then walk through a couple of examples of, I would say, reliability problems in the data center space of relevance today, and give you two case studies of how this was done, one from a memory side and other from the compute side, right? So before I move on, I just want to acknowledge that what I'm going to talk about has been contributed by a very large number of people at AMD, within the memory industry, as well as collaborators at universities that we have been working with on this research. So I'm the mouthpiece of, I would say, the collective contributions of all these people. So let's begin in CS 101, right? This notion of abstraction, it came up in the keynote, Professor Amarasinghe's keynote on Monday as well. But let's look at abstraction from a sort of concept of computer design, right? So what you're really doing here is you're taking electrons, the very fundamental level, and building designing a computer system, and that's really hard to do. So instead, we break the problems into different layers in the design, from devices, circuits, logic, architecture, and on the different software layers. So the further down you go in this abstraction stack, the more physically, that's the ground truth, the reality, the physical realism is greater. But the further up you go, it's easier to reason about design. It's more scalable. You can think through things like large-scale design, programmability, and things like that, right? Now, if I take this logic layer, the concept of a bit, and just take the notion of a bit, with this sort of an abstraction of a bit, you can build primitives and operators which define all the operations for compute, for your memory, as well as communication, and collectively put these things together, they form a specification, and this specification is your architecture, right? Now, once you have the specification, and once you map it back into the physical world, once you implement it, let's say as a chip or things like that, this abstraction relies on certain kinds of behaviors from those layers below it. For example, if you're thinking about compute and you say something like an adder, if you give the same values, it should give the same sum, and the sum has to be correct. And every single time, it should behave the same way. If you write a bit or a group of bits somewhere and you didn't manipulate it, it should always be there the way it was when you left it. If you transmit a bit or a group of bits from a source to a destination, it should make it the way you sent it, right? So it relies upon these kind of behaviors. But the truth is that these expectations may not hold in reality as you go down the stack. And one of the reasons they may not hold is you could have faults in hardware. So an example of this physical things which can happen is you can have things like high-energy neutrons or alpha particles, which are just around us, always have been. And these can interact with your elements at your physical level, and they can lead to a spurious bit flip in a storage element. They could be defects in your hardware. And these defects can affect every component of your design, from your interconnect, your logic, as well as your storage elements. So And there can also be effects where things just happen over time, wear out, and effectively behave like defects in some way, shape, or form. So all these gremlins actually happen at the physical level, at these individual, which can affect these individual components. But when you start putting together systems like servers and data centers, all these effects get magnified, right? So let's say X is the rate at which faults happen in any one given circuit element, be it a wire or a transistor. And if you look at like SoCs today, you have order of like 100 billion or more transistors in a given socket. And a data center may have million or more of these sockets, and all these numbers have been growing over time, right? You have more chiplets in a socket, and then you're integrating more and more of these components. So the net rate at which these systems, at the full system level, you experience falls is really a multiplier of these effects, right? And if you think about it, if you have to cope with this problem, reducing X is really hard. In some cases, X either maybe stays constant or even gets worse over time, depending on what the root cause is. So if you really have to give this expectation that things are behaving themselves at these lower layers of the stack, you have to really design a resilient system. You have to explicitly engineer systems to behave that way, at these, to give this illusion of everything is OK at the higher level, right? And this notion of a resilient design, before I get into it, I've been using this term false quite a bit. I just want to precisely define a couple of terms which sound like synonyms, but they are not, right? So the term fault is you can think of it as the thing that goes wrong at the physical level, right? The particle strikes it, and these bits are changing, a defect happens. So, and these faults are associated with one or more root causes. And these faults may behave in specific ways. They may just be a random bit flip, they may just be transient, or they may happen all the time. And it really depends on the root cause. So particle strikes tend to be transient, defects tend to be permanent or kind of on again, off again in an intermittent way. And then error is a symptom of the fault, right? And the reason I wanted to bring this up is from a computer architecture perspective, if you're designing hardware, what we're really interested in is the fault. What is going wrong in the system? How often is it going wrong? So that you can actually reason about it and maybe design for it, right? Errors are important too, because that's what you see, that's what is the consequence, that's what causes problems, right? Now, and this notion of resilience is actually three different components. Reliability, which is the ability to provide correct service. So this is your things like your ECC, your parity, things which can detect and correct these faults so that they do not turn into errors or specific errors which you can deal with. And the second aspect is availability. Availability is essentially a fault has happened, a failure has happened. How do you keep going, right? How do you these things like restoration from checkpoints, graceful degradation is a term you may have heard of, like things like that fall into availability. And the third is serviceability. That is like, can you introspect what is going on in the system, and can you repair it or not, and reason about it? So it's really these three things called RAS. And these distinctions are key because sometimes if you cannot make things more reliable, you might have to push things into one of these other categories, and so on when you are architecting anything, right? So let's talk about this a little bit more. So if you take this, if you look at data centers of today and zoom in and see what do you see in the hardware, there are a couple of things you notice, right? So one is there is a lot of heterogeneity. You might have CPUs, GPUs, all kinds of accelerators, right? Interconnected each other. So you kind of see this increasing heterogeneity in the components being used in these servers, as well as there's a there's a trend towards greater integration of compute and memory. The memories, you want to bring the memory as close to your computer as possible. And paradigms like, for example, processing in memory sort of fall into this bucket of bringing things as close as possible. And so to do all of this in a practical setting, what happens is you'll see a multiplicity of components which may be manufactured by different companies. within the ecosystem, right? So the CPU comes from somewhere, the GPU comes from somewhere, the memory comes from somewhere else, and so on. So the glue that allows us to build these kinds of systems is industry standards, right? You agree on certain things which allows interoperability and some common good, and then you innovate on the other aspects of it, and you compete, right, for where they are. And one of the example of these industry standards, especially in memory, is a memory called high bandwidth memory, or HBM. So this is a memory you see pretty much used in most GPUs today and AI accelerators today, and for a good reason, right? So it's a type of 3D die stack DRAM. You have a wide interface which gives you a lot of bandwidth. You have a tight integration with compute. It's usually on something like a 2.5D integration on an interposer. So it's close enough to where your compute is, which gives you energy efficiency benefits and some latency benefits as well. And it has broad vendor support. All the major DRAM vendors manufacture this, and it's widely used. So I want to tell you a story about RAS in HBM, right? So before I go there, let me tell you, again, for those who may be unfamiliar with HBM and its sort of its lifetime, it's been around for a while. So the first HBM standard was released in 2013. And then there have been newer versions of the standard. So HBM2 was announced in January 2016. There was a speed bump of it. Architecturally, it's the same spec, but there was a speed bump in 2019. HBM3 in early 2022, another speed bump. And just middle of last year, HBM4 was announced as a spec, right? So just to give an idea of where these are in systems, real systems. So HBM2 is used in Frontier, which is the number 2 on the top 500 supercomputers. It used to be number 1. So some variation of HBM2 is used in that system. And the fastest supercomputer per the top 500 list uses a variation, GPUs with this HBM3 memory, right? But of course, when I think about a supercomputing sort of model, the thing which, the biggest workload with supercomputing is also used is, of course, AI training. Right? And this graph shows sort of a chronology. X-axis is time. The y-axis is the number of either GPUs or other kind of accelerators being used to train AI models. And as we know, AI models have been growing bigger and bigger and bigger over time, which requires a larger and larger of these effectively supercomputing clusters in order to train these GPUs, right? And just to put and again, so early 2022 was when HBM3's spec was released, right? So I want to tell you a story about going from HBM2 to HBM3, right? So when we were working on what needs to be HBM3, and we obviously wanted to enable what we see happening in industry right now. We wanted this memory to deliver the kinds of performance and benefits that the scale of supercomputers you see today in AI training as well as in high-performance computing being used, right? So that involves a lot of different aspects of design of the memory. But when we were looking at the reliability aspects of it, there was a problem, right? So in this graph, it's similar to the previous one. X-axis is now the number of nodes, and each node is sort of like an AI HPC-style node. The y-axis of this graph is the rate of uncorrected errors from your memory at the full system level, right? So this is taking HBM2 and all the ECC, I would say a sort of a typical way in which the ECC gets used in HBM2. I'm sort of leaving out the details from now. And we projected what might be the rate of uncorrected errors coming out of HBM when we start building systems of the scale that we see today, and it's going to keep scaling. What we see is, if you hit that 10,000 cluster number, you get an uncorrected error almost once per day. And once you go to this 100,000 thing regime, every few hours you take an uncorrectable error. And again, from an AI training perspective, this directly impacts the goodput of your system, because every time you take an uncorrected error, checkpoint, restart from a checkpoint, you're wasting time on I/O instead of actually training. There's things, right? So we saw this, and we said, OK, we have to let's try to do something about this, right? Or let's explore if we can do something about this, right? And the other aspect with HBM is from a sort of a serviceability viewpoint, right? So if you take, I mean, all memory is expensive these days, but if you look at a DDR-based server, right? If you have some sort of failure in your memory that you cannot write through with ECC, you can pull it out, put a new memory DIMM in, right? Whereas with HBM, because it's a tightly integrated memory, if you have some sort of a failure that you cannot cope with in that HBM, you have to throw the whole SoC out. That's a very expensive GPU or accelerator you're throwing out because of like potentially one failure in your memory. So that's not so great if you're trying to build large-scale systems and things like that, right? So these are all the problems we were staring at. And we said, OK, what needs to be like the solution direction we want to go? So if you sort of write down the solution considerations, you can sort of break this down into requirements and constraints, right? The requirements is we wanted to do better than HBM2, but in terms of error correction so that we don't keep taking so many uncorrectable errors. We also want to have robust error detection, right? So silent data corruption is the cardinal sin of RAS, and we want to we'd like to architect the memory so that you minimize the likelihood of that as much as possible for these systems at scale. And another thing which was sort of happening when we were doing this in this time frame is DRAM scaling faults, things like variable retention time falls and things like that, where it was the memory industry saw that these were going to be there's going to be additional sources of faults in your DRAM that you have to deal with. Now, what are the constraints, right? And these are constraints which we had to take into account if we needed to see a light of day for any research to actually turn into real world impact, right? So one, this whole ECC solution had to be restricted to 48 bits. If you're really curious what's so magic about 48, I can answer it in the Q&A. It's a legacy thing with HBM2. So n number of bits where that n happened to be 48. There was also a concern that the DRAM, the true scaling fault rate of DRAM, you didn't want to be able to reveal that. That was a business constraint coming in from the memory manufacturer side. But business constraint or not, all of these are real-world constraints you have to architect towards. And there was a bunch of things that you cannot do. Like, for example, for RAS, you can't just add DRAM pins. And that is true not just for HBM. Any memory, when you want to sort of do it, you can't add pins. You can't change the channel architecture. You can't just change burst lengths. Whatever you do, the power performance area overheads have to be acceptable, acceptable to the manufacturers as well as the end users of these systems. And eventually, the solution has to be standardizable. What that means is that all the parties in JEDEC, the memory industry, the SoC companies, as well as the end users, the hyperscale companies who are all part of it, everybody has to give a thumbs up to it. It has to meet the common good in all of these things, right? Now, DRAM reliability is not a new problem, right? And we all stand on the shoulders of giants in this community, right? And there have been a lot of good papers written on DRAM reliability over the years. I'm just showing a few, and this is not an exhaustive list of papers. There's been a lot of very good work done on DRAM reliability in the computer architecture community. This looks at everything from understanding these DRAM scaling faults and what to do about it, things like the need for in-DRAM ECC, various ways other than ECCs to deal with these kinds of faults, and some very interesting ways of designing ECC schemes to have high robustness and still respect various constraints within the DRAM protocols and things like that, right? As in the context of both die-stacked as well as other kind of DRAM. And I would say the prior research was foundational, right? And we studied it, we looked at it, and we said, okay, are there things we can draw from it? Is there inspiration? Is there ways in which we can take some of these things and turn it into practical solutions? Because people are given a lot of thought and study to these problems in the past, right? Well, it turns out, yeah, some of the things good, but not all the things. So it wasn't quite the pieces of the jigsaw puzzle didn't quite all fit together, but there were certainly a lot of good elements in many of this prior research to do. So how did we go about doing this, right? So let's take a look at what is inside a DRAM chip, right? So there is a hierarchy of interconnects, all the different word lines and bit lines, which eventually come down to your DRAM mats. And the DRAM mats at the intersection of your word line and sort of a subword line within your mat are your DRAM cells, right? And then you have your sense amplifiers and things like that. Now, if you ask the question, what could fail in this DRAM chip? Anything could fail, right? And based on what fails, they manifest as certain. So based on the faults you see, they manifest as specific kinds of either fault patterns or if you view it as an error, they manifest as different patterns from, for example, viewed from the memory controller if you look at what these things look like. For example, if your bit cell fails, or if something is happening in your memory bit cell, that looks like a fault in a single bit. If you have a fault in something like your bit line sense amplifier, it still maps to a single DQ, so it looks like a column, bits, all the bits lined up in a single column from sort of a row bank column addressing perspective of failing. Now, if you have something failing in a higher level, in an upper level of this interconnect, like for example, if you have a fault in either a subword line driver or a contact point, they all kind of look like faults mapping to a single row. And if you have fault happening at something like a main word line, it looks like a large number of bits in a bank are all showing an error. So it looks, so you can sort of call that a fault at the bank level. Now, all this is fine. This is all nice as sort of theoretically thinking about it. The question is, we were asking like, what really does happen in real systems? Now, it turns out one of the nice things is for well over a decade at AMD, we have been collecting data from large-scale systems and studying the fault behavior of these systems. And we've been doing this, I think, at this point, over 14 years. This graph shows x-axis is different memory technologies over time, starting with DDR2. Effectively, you can think of the x-axis of this graph as time, right? Evolution of time. And the y-axis is the breakdown, the percentage of each of these kinds of faults that we have observed in these systems. Every one of these bar graphs has an entire paper behind us, so there's a whole story of which systems we looked at, how did we do it. I've cited the papers where you can get more information about these studies. But effectively, if you look at this graph, what you see is that the lower portions of this graph, you see a lot of these single bit, word, and column faults. All of these are basically single bit type faults, is correctable by like a sec-dead style ECC. And then you see these other faults, which are like row, bank, and full device, like much more pervasive sort of fault mode. So in HBM2, the HBM2s, for example, if you think of the best kind of ECC you can do with the bits there, you can correct your bit, word, and column faults, but everything else is uncorrectable. Maybe you can detect them, but you will still get an uncorrectable error, and you get that graph which I showed you if you sort of use the statistics and plot what things look like. And another thing we have studied, we have found in many of these studies is when these multi-bit faults do happen, they tend to be kind of sticky. They're either permanent. It's always like when you access it, it's always you end up getting an error if your access is addressed, or they tend to be intermittent. It's on again, off again, on again, off again, sometimes turning permanent after a while, right? So we had these statistics. We looked at this, and we said, okay, let's see how these actually map to the physical fault boundaries that you see in DRAM. And one of the nice things is when we worked on HBM3, this was done through JEDEC, so it's a collaborative effort with the memory industry who bring a lot of domain knowledge as to how these faults actually map to the physical boundaries of the DRAM dies and things like that. And it said, okay, if you put back this cartoon and put this graph on it, what is the next frontier, next boundary of error correctability that might be useful to get, right? And what you see is that it's this purple area, the row faults. This is the DDR5 data, the most recent data. It's like a large number of these faults are row faults. Then the question is, row faults could be any physical thing. So we studied what exactly physically is happening when these row faults happen. It turns out these are what are known as subword line arm faults. So these are where you have a driver which is essentially connecting, let's say, one subword line connecting one mat and another subword line connecting another mat, if you think of these two things as mats. And that contact point between the driver and the mat, if it has some sort of marginality, that it looks as if all the bits connected to the mat are in error when you access it. Right? It gives an apparent look, but it's really that thing. And that could be any number of bits, right? Depending upon the manufacturer of the DRAM, particular SKUs, and things like that. So what we did is we said, OK, let's come up with a scheme which co-designs your DRAM die and your ECC scheme. And really what we said is, what if you can partition your DRAM die in such a way that anytime a subword line ARM fault happens, it's constrained to a very specific number of bits, right? And what we found out by doing a lot of studies of what you can do, what are the area overheads, all the PPA studies with the memory industry is like, the common good we saw is like you can bound these to 16 bits, right? Now with a 16-bit fault, if you understand like how symbol ECC codes work, you need twice the, if you have n number of bits, you need twice the number of check bits to correct such a fault with something like a Reed-Solomon code and things. So with 32 check bits, you can correct it, right? And then I said there's this keep things within 48 bits was this magic thing. So what then it gives you is like you can use 16 bits, and you can use it for anything, but it gives you an ability to enhance the detection capability of your ECC code, right? Just a little historical thing, the 32 bits was the original HBM2's total number of ECC bits, except the additional 16 bits came about because there was already a need for an in-DRAM ECC, which was identified, which was going to be a 16-bit code. So we worked within the bit budget of what was allowed if anybody was to listen to us in industry to get anything done. So what we then landed up with is a two-level ECC code, which should be familiar for many people who did research on the need for two-level ECC codes in the past. But it was done here in the HBM3 context. So there's an in-DRAM ECC, which now becomes a Reed-Solomon style ECC. And we had to do a lot of work to make sure that the latency and power and all of those things was not going to be a problem, right? So there was a lot of pathfinding studies with the memory industry. And so you can correct now these row faults, this most common type of row fault. So you move the frontier of correction. And anytime you end up, the in-DRAM ECC either detects and or corrects, there is a real-time transparency back to the host memory controller, letting it know, saying like, hey, I did this. This action happened. And this was done without adding any pins at all, because it turned out that when we move around where these ECC bits happen, we free up some pins from the original HBM2 thing. So no pins were added. We changed the signaling definitions of some of the pins and just worked through the logistics of that. And these 16 extra bits can go to the host. And you could, for example, do something like a CRC, a cyclic redundancy check code. It's a strong detection code, which can, you can build very high detection capability ECCs with it. And the reason this was nice from a standardization perspective is the in-DRAM ECC and the host ECC are orthogonal. So the internal code, there's separation of concerns. The internal code in DRAM is a correction code. It does some detection. The external code doesn't have to do any correction. It can be a purely detection code. So you don't want ECC codes trampling on each other, because bad things happen when you do that. And every DRAM company, as long as you correct 16 bits, how they implement it, that can be it's up to their choice. And what the host does, like an AMD memory controller does versus somebody else's memory controller, the standard doesn't dictate, right? You have 16 bits, do with it whatever you want, right? So you can independently evolve the ECC, which allows for standardization, right? And so long story short, so in terms of how good is this? So when we did a projection of this back in 2021, before several months before the HBM3 standard was closed, we found that the uncorrectable MTBF, depending on which field data set you use, anywhere from 7 to 10x reduction, about an order of magnitude reduction in your uncorrected error rate, which it moves the needle, right? And it moves the needle, and it's something which we can actually it's acceptable, and you can make it practical and build real devices out of this, right? So again, so this was adopted into HBM3, and it's any GPU or AI accelerator today is likely using this ECC. It's probably many of them are HBM3 based devices. So if you want more information on all the constraints and the whole journey and the trials and tribulations and technical analysis leading to HBM3, so there's a paper in Computer Architecture Letters in 2021, which you can see, but there are also additional papers from the memory industry, which gives you more details about how they took that architecture and those sort of requirements and translated it into actual circuit designs and all the overheads and things like that, which have been published. And I should also say that when HBM4 spec closed last year, this exact same RAS architecture was carried over into HBM4 as well. So all the future accelerators we'll see with HBM are going to carry over the same ECC architecture, right? Having said that, I would say there is still a lot of, I would say, research needed to improve the resilience of DRAM, HBM specifically, but DRAM in general, right? So the work is not done, right? We still need a lot of work. So I just want to talk a little bit about what I think might be some directions which is useful to pursue, right? First is I think we definitely need more field data. This is probably on industry to do, right? Because industry we build the silicon, other companies deploy it at scale. So certainly to my industry colleagues in the audience, if you have opportunities to put more data out, please do, because I think all data is valuable, especially I'd say to the broader community where access to data is very difficult. We have done all we can, and we will continue to do what we can from the company. But I think we need a village of data for these studies, right? So the second thing is it's certainly, I think there are opportunities to build a stronger ECC. In DDR systems, the gold standard is an ECC known as chip-kill. A chip-kill ECC can correct any fault within a single DRAM device. In an HBM context, that means any fault within a single die is correctable if you could have chip-kill. True chip-kill is extremely difficult to do with a die-stack DRAM's architecture, and I can talk about that separately. But anything we can do to improve the ECC, again, we did what we did as industry. Please look at it and see if you have other ideas, other ways to approach the problem, but being mindful of the constraints. It's hard, but we're a very strong technical community. So I certainly appeal to the community to look at this problem, right? But you can do other things too. For example, where the ECC itself might not be the way to address a problem, there are other ways to manage faults in system. For example, you can offline things which are faulty. You can do things in hardware like row repair. You can do things at the operating system levels like page retirement. And there's been some recent papers which also show that maybe some of these larger faults are predictable from these smaller faults. And I think exploring that in more detail and seeing if that leads to something viable, I think is certainly worth it. There is some data out there which, in fact, there was a paper at HPCA as well, which started looking in that direction. So certainly, that kind of work is useful, especially if you can ground it on field data in sources, right? And finally, can you really do a field replaceable HBM? Can you really pull it out like a Lego block from your HBM? I think it's a great vision to have. It might require some interesting packaging technology, but again, I think it's an open research question worth seeing where we can go. Now, these things may sound really challenging to do in the abstract, to look at it as in a sort of an application agnostic way. But in my opinion, if you constrain the use cases of where you're doing it, you may have some traction. For example, if you say, I'm going to look at only AI, maybe only AI training or only AI inference, and even this is quite a large volume of this HBM deployed at scale. If I take into account those kinds of workload or use case constraints, does it open up some degrees of freedom to optimize the problem? There may be, I think there may be some ways to do it. And one of the fun things I do, in addition to my work at the company, is I'm also the editor-in-chief of IEEE Computer Architecture Letters. And Cal gets a lot of, I would say, early ideas, quite bold thinking on future architectures and things like that. And I get to see all these papers coming in as EIC and what happens. And I found that there are a few papers published recently in Cal which may give little little hints as to where things might be going. So for example, there was a paper by Chia et al. This is a paper from Rensselaer Polytechnic and IBM, which talked about, instead of, if you consider AI inference, there might be ways to construct ECC by increasing the code word size, but then you end up in some performance problems, and you can look at, it's almost like a storage kind of way of looking at ECC in an HBM context. Interesting lines of investigation. And there was another paper by Wu et al., which was a paper from NYU, Princeton, and Cornell, which said, OK, if I have optics, I can maybe move the HBMs off the shoreline of the GPU, and I can manage its performance for LLM workload. It's nothing to do with reliability, but ideas where you're just moving that HBM away from where your socket is and trying to do things. You could layer on it and see, there might be reliability ideas to build on it. And just a couple of days ago, a paper got accepted from SK Hynix, which was looking at the use of high bandwidth flash in addition to HBM, and which can significantly reduce the amount of HBM, and you can have high bandwidth flash, but you end up with all sorts of performance issues to deal with. And flash reliability has been extremely well studied in the storage community. I was a storage person before I came into this, so there's a lot of research in other areas and these new technologies, which just take a look at it. Think about whether it gives you some ideas on how to make things more interesting, right? Just my 2 cents there. OK, so backing up from all this, right? So our mission, when I say our mission, I'd say a mission as industry, is that public trusts compute, right? And trust means different things. It's security, privacy, and so on. Reliability is one of the ways you trust compute. And the question is, did industry achieve that mission of late? Well, there were some papers published a few years ago from the hyperscalers, from Google, Meta, and Alibaba, which suggested, maybe not, right? So there was papers which talked about the occurrence of silent data corruption on high-performance CPUs deployed at scale, and this rang alarm bells, right? It put all of industry on note. And when this happened, of course, the question was why? Why did this happen? What is the root cause? Where is the boogeyman here, right? And there have been a lot of studies over the last few years within the company as well across industry in various forums where this has been discussed. And one of the conclusion, sort of a consensus conclusion that we have come to is one of the key root causes of this is what is known as small delay faults due to what are called marginal defects, right? So there's a bunch of buzzwords there. Let me explain what this is, right? So the way to think about small delay faults is, so take this cartoon. So let's say you have a storage element. You have a fan-in cone coming into the storage element, and then you have a path going outside it. I know I drew a figure just like this with a lightning strike on it and said that's particle strike. Well, you can randomly flip a bit. But the way to think about this is, let's say on that fan-in cone, there is a defect of some type, right? Now, that defect, it might add a small amount of delay to that path, right? So if you look at it more from a timing perspective, let's say I draw the diagram, but I now look at the timing slack on all of those paths. If I add a very small amount of delay on a path which has a lot of timing slack, you may not have any kind of a setup time failure or anything happens on it. But if the delay added exceeds the slack of the path, that is, you get a negative slack, you can get a setup time failure, right? That flop might latch the wrong value. It might transmit the wrong value. And so that's a small delay fault, right? From a defect known as a small delay defect. And the reason it's called a marginal is that what we have noticed that these faults are intermittent in nature. They seem to get activated by things like temperature, droop. So under certain kind of conditions, these things tend to manifest. And if you sort of an example of this kind of defect, you can think is if you say you have 2 metal layers, and you have a via connecting it, and there's some sort of deformity in that via happening at the physical level, the resistance of that via may change ever so slightly to the point at which, that if that via is on that cartoon's fan and cone, you could be in trouble, right? Now, so when you talk about defects, you immediately enter into the realm of testing, right? So typically the way you deal with defects is through testing, right? So let me walk you through what is typically done in an industry flow, right? So you fab your wafers come back, you do some kind of testing on the wafers to look for defects, right? And you find some defects, you toss some things out, you have some yield loss which happens at that point, right? What passes that step, you take your wafers, you build your chips, you build with your packages, you can do additional testing on the packages as well. You might find more defects, faults and things happening, toss a few things out, you incur a loss, but there's some packaging cost loss which you incur. Then let's say after that stage, you ship a bunch of these chips to a customer, right? There might be additional acceptance tests done on the customer side as well, and you might find some more failures and things happening. So you have a return to manufacturer loss, like things more fail out. After that, those chips, what is remaining goes into your fleet, into production, and one of two things could happen. One is the RAS features you put in there catches it, in which case it's not you detect it, maybe you even correct it. But if it bypasses your RAS features, your RAS doesn't catch it, the worst possible outcome is a silent data corruption, what I call the cardinal sin of a reliability design, right? So in general, when you go from the left side to the right side of this image, the cost goes up and up and up. And in fact, the cost of SDC could be way higher than any of these things previously, things like that. But so really what you want to do as much as you can is to improve your detection, move away from the rightmost point as much as you can, right? Now, one of the things you can do is extend your testing into production, and testing becomes a continuous process. And there was a very nice paper presented on this at the best paper session at HPCA on Monday from Meta and MIT on why you need to do this. What is the ROI to be gotten? And there was a lot of good data in this paper, so I suggest that if you're interested in this topic, to read that paper to see the value of online testing and what it can do. So continuous testing, but what you can additionally do is to look at the RAS of the processor and say, can I actually improve your detectability of these new kind of fault modes, right? These SDF kind of fault modes. So let me walk you through how RAS is actually done, sort of, and explain what we have to do, right? So let's say you want to architect a RAS feature. So let's say this square is your core or your SoC, and I want to put RAS in it. For most of the server cores out there, the way it is done is you take each and every hardware block in your core and say, what should I do with this hardware block, right? So how do I protect it? Do I add, and protecting usually means you take the state of that hardware block, you add these additional bits, just like you did in the HBM case, and add some additional logic, and based on what you're trying to do, are you trying to do parity here? Are you trying to do sected ECC, something stronger, something different, depending on what it is. So the toolbox of all these redundancy and reliability schemes have been around. It's been around for decades. It's been used in different ways. But for every block, you sort of ask the question, what do I do with this, right? Or do I even need to protect it? And you don't do this in sort of an ad hoc way. And this is usually guided by some sort of a quantitative methodology, some kind of a fault model, which tells you for every block what is the desired thing to do, and then you make your trade-offs, right? So let me walk you through how this is done today in industry, right? So let's take the design timeline of any core. So initially, you come up with the initial definition of your architecture. What do I want to build? And then eventually, you build the thing, and you ship the customer silicon, right? So for RAS, what you really want to do is to get a head start on this thing. You would like to define what you want to do for your RAS when you're defining the rest of your architecture specification. Anytime you start delaying problems happen. People are like, no, I can't put this in. Schedules will slip. Good luck. Let's see you in the next core, right? So you really want to intercept RAS as a first-class architecture design decision as early in the process as possible. And we can do that today for software as particle-induced transient faults. There was this methodology called architectural vulnerability factor, AVF, which was developed at Intel, I think, at this point, 2.5 decades ago. on how to reason about faults in the architecture systematically and quantitatively. It's become an industry best practice. So we can do this for SER, right, or for soft errors. But with this new defect problem, what happened is papers got published saying, wait, silent data corruption is happening at scale. So it's already everything happened and this thing was already deployed at scale. And then we are sort of working our way backwards, right? So I say, oh, OK, now from this field data, we can get some understanding that, OK, things are happening. And maybe from the silicon designer side, if you get access to the silicon, you can do things like physical failure analysis, things like soft deflect localize. There's a lot of different ways in which you can look at the silicon and see what is going on actually in there. And we learned that, oh, a lot of these things are these defect-induced faults, small delay faults. These are all been good insights, but these are all post-silicon insights, the post-mortem insights, if you will, right? So this silicon is already gone. So the question we wanted to ask ourselves is, do we really have to do it this way? Is testing the only thing we have to do? Could we come up with a fault model just like AVF, which we can use early in the design to be able to guide the design of the core to be tolerant not just against SER using AVF, but also against SDFs and be able to evaluate all the trade-offs. So we've been collaborating with MITs, with Mengjia Yan and Joel Emmer, and we have developed a methodology known as delay AVF, and this is delay AVF as in an AVF for these small delay faults. And this is work which is really driven by the students, Peter Deutsch and Vincent Ulich, whose photographs are up here. And basically, so here what we did is we asked a question. So delay AVF is the probability that if an SDF was to happen given in a block, in every site in a block, if an SDF happens there, does it manifest as a program visible error? And we developed this methodology based on the RTL of a processor. So it's still pre-silicon at this point. And based on the RTL, and there's a lot of details on how do you reason about, how do you do this tractably, and how do you figure out what the delays are. I'll refer you to the micro paper on all those nitty-gritty details of how the methodology works. But one of the key insights from the study when we applied delay AVF is we said, OK, if I take a processor core, I look at the AVF of the core, which is for particle-induced soft errors, and this delay AVF, which is a small delay faults, what insights do we get? So we did the study on an open source RISC-V core. So the x-axis here are some different structures in that core. The y-axis is sort of the normalized delay AVF to AVF. So for some conditions of timing of the core, is that the key insights we got is that when you study the AVF of the core, you get a certain rank ordering of which structures are most important. Well, you can rank order the structures in terms of the AVF, which tells you how important they are in terms of its impact on affecting it. So if you leave it unprotected, this is how important they have to protect it. It gives you a prioritization, which is important in design. But if you looked at the delay AVF of these structures, it gives you a different rank ordering, right? So you can't just take the AVF and somehow squint at it and be able to design for SDFs. You really needed a first principles approach, which was a key insight coming out of this study. And of course, this was done on an open source core. The question you may ask is, OK, what about big production cores, big x86 CPUs, production EDA tools? While we don't have a paper on that, I'd like to say that we have been exploring this methodology for larger designs. And we have made a lot of traction internally. And I really want to call out the work done by Peter, who came in from the outside after published the work to translate the research into practice internally for our designs and tools, as well as some additional excellent work which was done by Min Bui, who's a master's student at UC Santa Barbara. And so we made a lot of traction in-house, and hopefully at some point we'll be able to say more. But this is a methodology that we have been using internally to guide, to pathfind for resilient design of our cores, right? So, and coming back to the testing, right? So there are really two ways you can, two sort of paradigms for testing silicon, right? One is structural testing. So this is testing, you might have heard of scan testing, maybe, right? So here what you do is you put your chip on a tester, You use fault models, something like, for example, for delay faults, it will be like a path delay fault model. And then you can generate very high coverage tests to see if, if there's a defect in there to be able to catch it. It's very expensive to do. And it's done under very controlled operating conditions, which may not actually trigger some of these marginal defects, which happens under mission mode. But it's a very powerful way of testing. The other is what is known as functional testing, which is essentially run programs. And these programs are crafted in such a way as to somehow elicit the faults from these defects and to manifest it. And functional testing is really the only viable, is also amenable for testing at any stage of the process, manufacturing as well as, and the fleet and online testing. But it's very difficult to craft these functional tests and reason about what coverage you can get out of these tests. It tends to be laborious. You don't really have automated tools. So we asked a research question, can you actually develop high coverage functional tests, which in an automated way, which can be targeted, right? I can say, I'd like to write a functional test targeting, let's say, the L2 cache of this particular core for a small delay fault model or a stuck-at fault model and stuff, things like that. So in this, we have been collaborating with Professor Dimitris Gizopoulos' group at the University of Athens. And so we developed this methodology called Harpocrates. And this is, again, led by students, Nikos Karistinos and Odysseas Statsopoulos. And so the idea here is if you want to write a test for, let's say, targeting a structure on a given CPU, and if you know the architecture of if you know, let's say, the architecture design and microarchitecture of that CPU to some extent, you can borrow some ideas from fuzz testing as well as genetic algorithms that says, OK, now I have a simulator of that CPU. And I can essentially write programs which, and using a sort of a mutation method, you write a program and you grade how well that program might be able to take a fault and then make it into a program visible state. And the nice metric is AVF is that metric, or delay AVF for SDF. So can you essentially write a test which maximizes the AVF or delay AVF of that particular structure? So you need to, if there is a defect in there, sitting in there, you can tickle it and you can likely get an observability of the effects of that through a testing methodology, right? So, we have a couple of papers on that at ISCA a couple of years ago and at IEEE Micro coming up. And so we did this study using a simulation-based study, and we compared it to some other open source testing methodologies, which have also been published recently, and we found that the coverage that you can get using Harpocrates can be significantly high. And we have published this. And again, the question is, OK, this is the simulation-based study. Well, how does it actually work in practice? Does it actually work? And I'm happy to say that we have tested this on several CPUs in-house. And we have found that this methodology is promising. It can catch defects in real silicon. We've gotten a lot of learnings on it. I won't say too much about it because we are submitting a paper for peer review soon. So we'll let the peer review process play itself out. But yeah, so we have found, again, we have translated this research and we're translating this into practice and found promise in doing it. So again, from a suggested research directions, I have a few thoughts here. One is, I think we need a holistic understanding of root causes. We know what we know. We don't know if there's more things out there, more gremlins in silicon that it's not there. And to some extent, I think this is, again, on industry to be able to educate, I would say, all of us in the community. Right? Just like it happened 20-odd years ago when industry got together and we said, yes, we see that soft errors is the thing which is happening, because once we know what the problem statement is, the research community is extremely good in thinking about what to do about it, right? So SDFs, we know that. Is there anything more? I think it's good to know that. And once you know it, there's good work to be done in fault modeling as well as testing. Again, once you know, you can systematically do it. And as well as, even with something like delay AVF, it's RTL-based. Can you do things even closer at pre-RTL stages? It's a lot of open questions here, which I think is worth investigating for the broader community. And finally, of course, the big question is, I've been saying CPUs and things like that. What about AI? What about GPUs, AI accelerators, AI workloads? It's a lot of open questions here. So for this, the OCP, the Open Compute Project, we published a white paper. So there's a lot of lot of the voice of industry, if you will, at this point. So it's out there. You can search for it, and there's a lot of, I'd say, nuggets of insights, as well as some suggested research directions and problem statements. And I urge you to look at and see what interests you as well. In addition to that, I also want to say that there is a IEEE micro special issue on silent data corruption, which is either imminently coming out or have just come out. But most of the papers from it are already available to early access on IEEE Explore. Again, a lot of papers from industry. So for both people saying, like, I'd like to hear from industry what the problem statements are, there you go. There's a lot. It's from a lot of different companies out there, a lot of studies, a lot of data. Hopefully, you'll find it useful and interesting to think more about it. So I think I'll wrap up here, right? So reliability and resiliency are really important. You might not always think about it, but there's a lot of work which is done by a lot of people, so that those who are not working on reliability can do all the other great research that you do. But when new problems like SDFs happen, or architectures fundamentally change with really hard cost functions, there are lots of opportunities to do good work, as this community has done in the past. As many papers I showed, I think there's a lot of opportunities to do here. But again, to do this, ground yourself in data as much as available or provided. And then from that, you can systematically work your way towards root causes and then see drive remediations. And again, a lot of this work I presented would not have been possible if not for collaborations. All the DRAM field data came about because we had the fortune of collaborating with both the memory industry as well as people who deploy these systems at scale. So many of those papers were with the DOE National Labs, Google. And so again, partnerships and as well as the academic collaborations, for the many students out there, there's a lot of opportunity for you to do research. And again, together we advance. And with that, thank you, and I'm happy to take any questions.
Thank you. We have some time for a couple of questions, so if the people can line up. Yeah.
Moin Qureshi, Georgia Tech. Excellent keynote, Sudhanva. The way we have sort of figured out how to make unreliable storage work is by just having larger granularity, right? Flash has 1,000,000 times higher error rate, but we made it work. But somehow for memory systems, we are stuck with 64-byte line size that was developed 4 decades ago. Our workloads have changed. We have lots of spatial locality, right? Especially for HBM. What stops us from rethinking access granularity, which will reduce the cost of reliability, allow us to sort of think about other possible reliability solutions like RAID 3? Why are we stuck with the past?
Yeah, that's a good question, Moin. So the access granularity in many cases have been sort of dictated by what SoC companies have as the last line, the last level cache sizes and things, right? So one of the papers I referenced, which is this paper from RPI and IBM, they are exactly asked this question, right? So they said, okay, if you can't change the native access granularity, does the access granularity of your ECC have to be the same as the access granularity of your data, right? So you can have much larger code word sizes, which allows you to take the same bits but still have a much stronger ECC and things like that. And but then it brings this access granularity performance management issue. And there's some interesting ideas in that paper, which is why I highlighted it. I think what you said, if you can decouple the access granularity of data from what you need to do for your reliability, I think there's a lot of degrees of freedom. And then how to manage performance of these things, I think we know how to do that, right? We are computer architects. We have done a lot of work on how do you manage, even in the SSD space, right amplification, things like that. I think we have a lot of a framework to think about problems like that, and I certainly encourage it.
Thank you.
This is José Luis Avellán from the University of Murcia. Very excellent talk, so thank you very much for all these insights. So I'm just wondering, what does it happen in this new era of processing in memory, where you are including inside memory these DPUs, processing elements, this compute logic, in terms of resiliency, in terms of error faults, in terms of new techniques. So what are the insights, and if there are any kind of analysis that could help alleviate these new?
Yeah, thank you for the question. So processing and memory, I would say, there's a large number of architectural alternatives on what that actually means. But I would say one thing to keep in mind, I'd say a constraint I would put out there in doing that work is data is data. Whether it's accessed by your host or accessed by your PIM, it should have the same level of reliability. And that sometimes could be challenging depending on where your PIM units are sitting, right? So for example, if it's like HBM, where a lot of ECC capability is already in your DRAM, you could do certain things, right? But if you have certain PIMs where things are not sitting in your DRAM, but on the side of your DRAM, going back and forth can create it could actually wipe out any performance benefits which comes out of PIM, which is, I think, a challenging problem to look at. But I think if you set the constraint saying, how do I design ECC architectures or RAS architectures, maybe, where data is treated as a first-class citizen, regardless of who is creating, accessing it, or consuming it, it'll lead you a certain, you'll constrain your space of how you think, and maybe it can lead you to somewhere interesting. And certainly, I encourage that line of investigation. Right.
Okay, thank you very much.
Jung Hwan from Seoul National University. Very inspiration talk. Thank you. So in your early part of the talk, you talk about the kind of collaboration with other industry other than AMD through JEDEC. In the second half, you talk more about the collaboration with academia. As you know, for the first half for the DRAM or the memory part, what's the role of the academia if you guys talk within the industry between the kind of DRAM vendors and between the kind of the producers and consumers? So can you share?
Yeah. I mean, as I said, I listed a lot of papers, including one of yours.
Those are
right?
mostly from the industry.
So I would say academia in DRAM reliability, by the time HBM3 came along, there was a lot of very good research being done. And I thank academia for doing that work because it provided a good platform to start thinking about the problem. And in fact, if you look at those papers and you look at HBM3, you'll find a lot of things in there which resemble different parts of it, right? Now, the way the work was done, it's just a quirk of how it was done because of timelines with JEDEC. It had to move, and we needed to be done, so we worked solely within the DRAM industry. And I know the DRAM industry also collaborates. So, and JEDEC has this hub and spoke model. I think it'll be wonderful if industry standards bodies were able to bring in universities as part of the loop in the innovation loop, right? For example, in OCP resilience workgroup, universities are there's industry in there, but like there's been a lot of universities funded through that program, and there is a lot of cross-fertilization of and communication between industry and academia there. So. Certainly, if there are ways in which industry can be brought in the loop, and I know a lot of university, again, through Cal, I see a lot of papers co-authored from the DRAM industry as well as universities, so that is great, but if there's a way to systematize it and standardize it, sure, let's explore that.
I don't know where is the great place to talk about, but as you mentioned, the OCP, there are more kind of academia involvement is going on, but for the JEDEC, if you have any kind of chance to speak up, please do so.
Will do.
Thank you.
All right, that's all time we have. Let's thank our speaker again for his great talk. And this session is concluded.
A quick announcement. Someone left a nice black jacket on the boat last night. If you know whose that is or it's yours, please come see me. I'll hold it.
Let's see, does this work? It does work. Okay. Hi, everyone. This morning, we have a very exciting session on matrix and linear algebra algorithms. First up, we have a fantastic talk titled Towards Singular Value Decomposition for Ranked-Efficient Matrices, an efficient and accurate algorithm for GPU architectures. And the speaker we have presenting it for us is Shi Lu. Without any further ado, take it away.
Today I'm going to present our work titled Towards Signal Value Decomposition for Ranked-Efficient Matrix, an efficient and accurate algorithm on GPU architectures. In this presentation, we will discuss 3 sections: background, methods, and experiments. SVD is a fundamental tool for matrix computations. It appears in many applications such as no-rank approximation, image compression, matrix completion, and video background generation. Here is SVD, which stands for Signal Value Decomposition. It says we can write a matrix A as U times sigma times V transpose. From this table, full SVD keeps a similar error level across different distributions, and it is about 10 to the minus 6. This figure shows the performance of the crossover GSVD routine on an H100 PCIe GPU. We can see that when the matrix becomes larger, the running time increases very fast. At nuggets the matrix size, the time is about 175 seconds, which is quite slow. Also, the H100 PCIe GPU has a peak performance of 51 teraflops, but this routine can only reach about 0.5 teraflops. RSVD, which stands for randomized SVD. The main idea is instead of doing SVD on the big matrix A, we first project A into a smaller space and then compute SVD in that smaller space. First, we use random vectors and power iteration to get Y. Then we build an orthogonal basis Q from Y. After that, we construct a smaller matrix B equals Q transpose times A. Finally, we do a truncated SVD on B. The accuracy depends on 2 things: the number of power iterations and oversampling. With this method, the time cost can drop from m times n squared to about m times I squared. So it can be much faster for large matrices. From the table, RSVD has much larger backward error, so RSVD is usually used in applications where speed is more important than accuracy, or the task is not very sensitive to accuracy. Then we do an experiment. We can see that full SVD stays very stable at around 10 to the minus 6. Householder QB is also small, around 10 to the minus 4 to the 10 to the minus 5, and it becomes even better when the condition number increases. But for RSVD, when the condition number becomes larger, the backward error jumps to about 10 to the 2. That means, in this case, RSVD may give a wrong result. RRQR, which stands for rank revealing QR. The basic idea is QR factorization, but we also use a pivoting matrix P. So the formula is PA equals QR. RRQR is called rank revealing because after pivoting, the diagonal of R is usually in decreasing order. This makes it easy to see which part is important. So if we want to target rank K, we can keep only the first K part and drop the rest. Then we get an approximation P times A equals Q times R. Unlike RRQR, QB factorization discard columns during the factorization process. We compare the cost. RRQR is mn squared, but QB is mnk. So when k is much smaller than n, QB can be much faster. Next, we will introduce our method in the method section. Here we use this table to show a problem. The original QB SVD is not as accurate as full SVD for some distributions. Because of that, we propose an improved method. These are our enhanced methods. First, the original QB SVD uses the Gram-Schmidt process, which is not as stable as full SVD. So we make 3 improvements. First, we use block QB, so we can make it more efficient. Second, instead of checking the whole column of Q, we only check the diagonal elements of R. This reduces the cost from Mn to M. Third, replace Gram-Schmidt with householder transformation to get better stability, except for the bottom level of TSQR. First, we use blocking to speed up computation. Instead of processing the whole matrix at once, we split it into blocks and do QR block by block. Instead, in the end, we merge the results and get the final Q and R. This is more efficient, especially on GPUs. Second, we only check the diagonal elements of R. The diagonal values tell us how important each part is. If the diagonal elements is smaller than a small EPS, we consider it unimportant. Then we remove the related rows in R and the columns in Q. So this step is faster and still works well in practice. This figure compares naive QBSVD and householder QBSVD for different ranks. We can see that householder QBSVD constantly takes less time. This is introduced the math proof for our method. I will only present the key number. Other details can be found in our paper. If the jth column is dependent on the previous columns, then Rjj is equal to 0. If the jth column is dependent, then we remove the jth row of R and the jth columns of Q, and the factorization A is equal to QR still holds. The final is eliminating the columns of Q keeps the remaining columns orthogonal. Next, I will talk about TSQR. The idea is to split the matrix A into several smaller blocks. At the bottom, we have 2 practical points. First, we use auto-tuning. Based on the matrix size and the block size, we choose a good number of GPU blocks. Second, TSQR can achieve higher memory speed, so it can run faster on the GPU. Here we compare the runtime of TSQR factorization and our TSQR. The matrix size is n times 32. We can see that our TSQR is always faster. The speed up is 1.5 to 2.3 for different matrix sizes. From the previous results, when the rank is high, the SVD step becomes the bottleneck. The chart showed that the QB factorization is already fast, but the QB part costs much more time as the matrix size increases. So we need a faster way to finish the SVD step. Now I will introduce our EVD-based SVD method. The key idea is we use FP64 EVD to compute a more accurate FP32 SVD, including signal values and signal vectors. In this way, we get the SVD result, but we use FP64 only in EVD part to make it more stable. Here is a brief math proof that explains when our EVD-based SVD method is accurate and stable. The main conclusion is if the largest signal value is less than 5.3 times 10 to the 8, our method can ensure accurate signal values. Also, if the condition number is less than 5.3 times 10 to the 8, our method can ensure backward stability. So as long as largest signal value and the condition number are not too large, the proposed method works reliable in FP32. Next, we show our experimental results. We report two kinds of errors: backward error and signal value error. We can see that crossover's backward error is around 10 to the minus 5, but our method is around 10 to the minus 15, which is much smaller. For the signal values, our method also gives smaller errors across all distributions. Here we compare the runtime of three methods: FP64 crossover SVD, FP32 crossover SVD, and our EVD-based SVD. We can see that our method, EVD-based SVD, is the fastest across all matrix sizes. Next, we move to experiments to test the performance and accuracy of our methods. Here, we compare the runtime of three methods: our householder QB mixed SVD, RSVD, and full SVD. In both figures, our method is the fastest across all matrix sizes. Also, as the matrix sizes increases, the gap becomes larger. So these results show that our method scales better and gives the best performance for both rank size. The case rank equal 4K. Our method, householder QB mixed SVD, is the fastest. Besides speed, we also care about accuracy and stability. The figure on the right shows the backward error under different condition numbers. We can see that our method stays very stable at around 10 to the minus 6 across all condition numbers. Next, I will show an application of our method, image compression. Here we compress a 4K times 4K image using low-rank SVD. From the results, HQB SVD achieves good image quality, and it is also faster. So our method can give both good quality and high speed in image compression. Thanks for listening. Are there any questions?
Hi, Shilu. I have a question. Actually, in the real application, I think the low-rank matrix is very not very common. So, the advantage of your method?
Our method is the tips on various ranks. When we meet high rank cases, we will bypass QB factorization, and we only use EVD-based SVD. Like this figure, we can see that our EVD-based SVD for high-rank cases can still achieve good speed up.
Okay, thank you.
If not, let's thank the speaker again.
Actually, we don't really receive many questions.
Next up, we have another fantastic paper. This one, a diagonal block memory-aware polynomial preconditioner for linear and eigenvalue solvers.
Okay,
Take it away.
so yeah. So because first order of this paper is not able to join this conference because of the visa issue, so I'm going to present the work on behalf of the Xiaojian Yang, who is not able to join this conference due to the visa issue. So here are some of the contents of this presentation, and I will start from the background of this work. Sparse linear system and eigenvalue problems are central tasks in scientific computing. Above applications form the fundamental pillars of the modern HPC, with their computational cost often dominating the total runtime. Krylov subspace iterative methods serve as a main workhorse for the practical HPC workloads, and many iterative variants have been developed to address different application scenarios. However, the metrics arising from the real-world problems often have large condition numbers, which leads to very slow convergence if this method applied directly. To accelerate the convergence, preconditioning techniques are often employed. By introducing an approximate inverse of the sparse matrix A, the original problem is transformed into a system that is easier to solve. For example, in linear systems, a preconditioner can improve the condition number. In eigenvalue decomposition, the preconditioner can simplify the eigenvalues within a target spectral interval while compressing those outside it, thereby accelerating the solution process. Compared with other preconditioning techniques based on factorization or approximating inverses, polynomial preconditioners are easy to build, highly parallelism, and memory efficiency. Moreover, they can serve as both preconditioners and spectral filters. The basic components of the polynomial preconditioner include the polynomial coefficients and the key kernel called the matrix power kernel, or MPK. MPK applies a matrix A 6D times, essentially a chain of the SPMV operations. There exist many optimization techniques of SPMV, and several related work have been proposed at this conference. And also, however, for MPK, some researchers have gone beyond optimizing individual SPMV calls and focused on reusing the data of the sparse matrix A to accelerate the entire MPK computation. Next, I will introduce the several existing optimized MPK. The first one is level-based MPK, or we call it LBMPK. LBMPK maximizes the reuse of the matrix fragments in the cache by computing their contributions to all intermediate SPM results. As shown in the left figure, suppose the yellow matrix fragment is already in cache and has been used to compute A times X. Its results may then contribute to certain rows in the second SPMV to obtain A squared times X. And similarly, the new results can participate in the computing A cubed times X. The advantage of LBMPK lies in its high data reuse rate. In theory, if the cache is large enough, all MPK calculations can be completed by fetching the message from memory only once. However, in practice, cache capacity is limited, making it difficult to estimate the actual amount of the reusable data. The second type is forward-backward MPK, or we can call it FBMPK. FBMPK reuses the message fragments to compute only 2 consecutive SPMV. FBMPK first splits the message into the upper and lower triangular parts, as shown in the left figure. After the upper triangular matrix is used to compute the current SPMV, the lower triangular matrix can be used for 2 consecutive computations. The first is to compute the full result for the current SPMV, and the second to calculate its lower triangular matrix for next SPMV. In this way, the upper and lower triangular matrices reuse data. The advantage of FBMPK are stable data reuse rate and simple implementation. In theory, only D plus 1 over 2 matrix loads from the memory are required. However, the two methods share the common drawback that the data reuse introduces data dependencies. For example, suppose row I and J in the figure are intended to be the computing in the parallel. Due to the data reuse, row J might require the latest results from the row I, creating a task dependency between the two rows. Such dependencies can be complex and reduce overall parallelism. This issue is similar to another important sparse matrix kernel, the sparse triangle solver. Both LBMPK and FBMPK employ graph partitioning and graph coloring techniques to increase parallelism. However, these approaches typically involve significant pre-processing overhead, difficulties in selecting block sizes and the number of colors, and the introduction to inter-block synchronization, all of which present new challenges. To address the above issues, this work proposes a DBMPK. The core idea of the DBMPK, DB represents a diagonal block MPK, is to retain the data reused only within the diagonal blocks to avoid data dependencies. DBMPK splits the matrix into diagonal and off-diagonal blocks, with each diagonal block further split into upper and lower triangular matrices. During the computation, each diagonal block, LU, is handled by a dedicated thread, and a BMPK-style data reuse is performed within the block. The off-diagonal block E is processed as standard SPMV. Because diagonal blocks are distributed with both row and columns of the offsets, it avoids mutual dependencies. Another advantage of the matrix partitioning scheme is that it extends naturally to 1D distributed settings where the communication blocks F are treated as off-diagonal blocks. This makes the DBMPK easy to integrate into existing solver libraries and take effect immediately. This figure illustrates the computation workflow of the DBMPK. Comparing to the previous introduced BMPK, DBMPK simply computes the off-diagonal blocks in advance, and after the off-diagonal blocks finish computing, the first calculation of the diagonal blocks completes the current SPMV. Afterwards, it can be directly reused to perform the second computation. It may seem that a synchronization is required between the off-diagonal block E and the diagonal block LU. In practice, it doesn't need to be separated and computed independently. The matrix can still be assigned to computing resources according to a row block partitioning. This computation process is very similar to standard SPMV. Loading balance and other optimization techniques can also be employed in DBMPK. Simply considering the diagonal and off-diagonal parts separately during the calculation. We introduce an important metric called the diagonal block ratio, denoted as DIAG ratio, which characterizes the data reuse rate. According to the performance modeling, on the given machine, the peak performance of the kernel is proportional to its arithmetic intensity. Or we can here, and we call it AI. The AI stands for is of the standard MPK is the same as a single SPMV defined as ratio of floating point operations to the memory traffic, where we approximate memory traffic using the total storage of all metrics and the vector involved. The AI improvement of DBMPK relative to MPK can be attributed to the reduction in memory traffic. In DBMPK, a single loop consists of the one SPMV on the off-diagonal block E and two consecutive SPMV on the diagonal block L of U. However, the diagonal matrix load only once at the cost of storing one additional intermediate vector. Results represent the speedup of the DBMPK over MPK, and it depends on two key factors, the defined diag ratio and the average number of the non-zeros per row. Set it to be greater than 1, as long as this condition is satisfied, the memory traffic of DBMPK will be lower than that of MPK, and the performance acceleration follows. So next, we will evaluate the performance of DBMPK. We select 108 metrics from the sparse collection and evaluated them on the Intel platform and an ARMv8 platform. The polynomial degrees were chosen as d equals to 5, 20, and 40. In each subplot, the horizontal axis represents the diagonal ratio, and the vertical axis plots the speedup of different optimized MPK over standard MPK. Across all subplots, the speedup of DBMPK increases, the diagonal ratio grows. LBMPK and FBMPK may achieve high speedups on some metrics due to their high data reuse, visible as green and blue dots. But they also produce poor results on most metrics with speedups below 1. In contrast, DBMPK exhibits much more stable and predictable performance overall. Moreover, the performance advantage of DBMPK becomes more pronounced at higher powers, which aligns with the practical scenario's requirements. We first select 15 representative metrics from detailed analysis. The right figure shows that their performance on two platforms. We focus on the two bars on the right side of each matrix, which corresponds to the measured DBMPK performance and the predicted performance based on the standard CSR based MPK. These two results are generally constant. The left figure shows that the memory traffic of the several optimized MPKs relative to the standard MPK. Reduction in memory traffic is a main reason for their performance improvement. However, for LBMPK and FBMPK, lower memory traffic does not always translate to higher performance. For example, LBMPK exhibits even lower memory traffic on measure number 4 and 9, but its performance is still worse than DBMPK. The reason is that LBMPK and FBMPK introduce substantial synchronization within their algorithms, which reduces their bandwidth utilization. In other words, they fetch less data, but fetch it slowly. Since DBMPK only needs to split the matrix into diagonal and off-diagonal blocks, its preprocessing overhead is very small, roughly equivalent to 10 SPMVs on average. In contrast, existing optimization schemes rely on graph partitioning techniques whose preprocessing cost is often more than 300 SPMVs on average. Low preprocessing overhead is generally more valuable in practice. Finally, we examine the role of DBMPK in practical polynomial preconditioning. In practice, polynomial can be taken in diverse forms. For example, polynomial coefficients may appear in both real and complex forms. Due to its simple and efficient structure, DBMPK can accommodate these diverse forms. YHMG is a parallel algebraic multigrid library developed by our team. It implements various parallel algorithms optimized for memory access and communication, supporting multiple preconditioners and iterative solvers. This work integrates DBMPK into YHMG and compared against equivalent methods in advanced software libraries such as Trilinos. EVSL, and Hyper, end-to-end solution times are measured. The first application is solving sparse linear system using TMRS with a polynomial preconditioning. We adopt a polynomial method from the following literature, and we compared it against the equivalent implementation in training nodes. We evaluate the same 15 matrices using the previous MPK test. The polynomial degree is set to 40, driving the relative residue down to 10 to the minus 8. The results shows that the best implementation of YHMG achieves comparable performance to training nodes. Under various MPI, OpenMP, hybrid parallel configurations, and scalability tests, integrating DBMPK further improves the performance of the YHMG by approximately 20 to 30%. The second application is computing eigenvalues using Chebyshev polynomial filtering. The algorithm setup and the test metrics are derived from the literature. The order of the polynomial is typically ranged from 10 to 30. DBMPK improves the performance of the best YHMG by approximately 20%. Furthermore, compared to EVSL and its distributed version PEVSL, the optimized YHMG with DBMPK achieved up to the 30 speedup, demonstrating strong practical performance and scalability. The third application solves linear systems arising from the Laplacian 7-point substantial using multi-grid method, where Jacobi Chebyshev polynomials are used as smoothers. This experiment is conducted on the 128 computer nodes. Due to its optimized interpolation and communication strategies, YHMG significantly outperforms implementation in Hyper. Even considering only YHMG implementation, integrating DBMPK yields an average performance improvement of 34%. Moreover, the number of the iterations remains unchanged, indicating that the DBMPK maintains the convergence. So in the end, I'm going to summarize the contributions. This work proposes DBMPK based on diagonal and off-diagonal block matrix partitioning. DBMPK avoids data dependencies during the matrix data reuse and can be efficiently scaled to distributed systems. DBMPK can also easily integrate into existing solver libraries, achieving a significant performance improvements while maintaining the numerical stability. So that's all for the presentation, and thanks a lot. So, and also because I'm not very familiar with sparse solvers and also the preconditioning, so I'm not sure if I can really answer the questions.
Well, with that, does anyone have a potential question? If not, we can go on to the next speaker. Thank you so much. Okey-doke. So third up in our fantastic session going all the way through matrix and linear algebra algorithms, we have a speaker from the College of William and Mary, Andreas Strathopoulos, presenting a distributed matrix block vector multiplication in the presence of system performance variability.
Thank you.
Take it away.
Thank you so much. You already heard the talk title, so I'm not going to repeat it. This is work with my student Yu Chen Ma and my colleague Bin Ren at William and Mary. I do want to notice that 1693 is the establishment date of William and Mary, and this is the 1/3 of 1,000 years anniversary this year, so this is very interesting. So what this talk is going to be about is the basic operation that happens on iterative methods when they're dealing with dense matrices. This happens, for example, in kernel regression, Gaussian processes, many kind of statistical learning applications where the matrix is dense but created based on some other data, similarities or dissimilarities of data. You come up with these big matrices and you want to do some sort of solver with these, eigenvalue, singular value or linear systems. And you want to apply the matrix many times to a vector or to a block of vectors. We're going to deal with block of vectors here because of better efficiency. We're targeting sizes of 1 million or more. So if your problem is like 50,000, we're not going to look into this. There's libraries that do that very nicely. The question is, there are no libraries that do something for 1 million, 10 million, something that really puts a lot of burden on computers. As I said, we're going to use a block size B, so there's going to be maybe 10 or 100 or 64 vectors here, going to be multiplied by a matrix K, and they're going to give you a result R. A nice depiction, I'm going to come back to this picture later, is shown here. Notice that one thing that we cannot do is store a 10 million by 10 million dense matrix. So this matrix is computed on the fly. So that means the data, where the features of the data need to be compared and get dissimilarities of them, they have to produce something, let's say an element or a tile in your matrix. And then as you create this matrix, it's multiplied by the vector and it gives you the result. Now, this is distributed, so we are talking about MPI plus X. Here, it's going to be MPI plus OpenMP. We need modest size systems. We don't want to go million processes. We're going to do something like maybe 64, 128. If you can find a machine that does 256 nodes, go ahead. But most people don't have that big machines. So we're looking at this range of about 100 processes. We assume row distribution. I'll come back to this. We had a computer program like that a few years ago, and we experienced okay performance up to maybe 64 processes. And then the strong scaling started going away, and we didn't know why this was happening. We did some measurements in the beginning. And what this paper is about, digging into the reasons for that, and we noticed, and this is the thesis of this paper, that modest system variability, we're talking about dedicated systems, but thermal differences between cores create, I don't know, less than 5% system variability, can break your pipeline codes. The contributions of this paper is how do we diagnose that with simulation and trace tools, and how we tolerate it. Just to mention, we use block of vectors, so it's not a matrix vector multiplication, but it's a matrix times block of vectors, because that gives us better performance and also parallel granularity. And we're not going to use the 2.5D or 3D matrix multiplication algorithm, because at the end of the day, this is a tall, skinny matrix. It's not really, it doesn't have the aspect ratio that favors this type of codes. And at the same time, for the clusters that we're talking about, 100 of nodes, 1D partition can give you the opportunity of pipelining and therefore completely hiding your communication. That's what we want. If you're wondering what the pipeline method would look like, think of this V vector here. Every process has a part of these rows and also a part of these result rows. And what you do is you give to the left your part of V, you get from the right the part of B, you do your local computation, and you keep repeating this merry-go-round until the whole thing is done. Classical 1960s algorithm, nothing important here. The cool thing is, If the communication is not too large, we can overlap completely the communication, and that's what we want. There are two computations that we do here. One is kernel generation, and the other one is the matrix vector multiplication. So we generate, we multiply, generate, multiply. And once this phase or step is done, the next communication happens and so forth. The problem is, as we showed, we should be up to 128 at least processes be overlapping 100% of the communication. We have a little bit of theory in the paper that shows that we should not be seeing any communication, yet we have been seeing a lot of communication. So the question is, what was happening? So what was happening is, after a lot of tracing, we saw that there were some sort of stalls inside certain threads. The threads, even though it's a symmetric multiprocessor, do not all behave the same. Some of them get, as I said, some delays. And the worst thing here is this less than 5% variability, these stalls. If you apply them on a pipeline algorithm, they create this picture. This picture means bubble propagation. We all know that, right? Microarchitectures have the same problems. There's no reason why parallel computers don't. And that's exactly what is happening. So this MPI, this bubble propagation showed up as stalls in communication. But it's not communication. We should have been able to overlap this completely. So what we present here is how do we tolerate this variability? And we find 4 fixes. One is interprocess preloading. One is kind of unconventionally static scheduling and not dynamic scheduling. Cache-aware tiling and multi-versioning, as we're going to see later. So let's talk about preloading. Well, why do I need to have this give me, take pipeline? Why can I have queue buffers where I take many things from the previous guys and I send to many previous guys, and whoever gets done first computes its work? That's all we do. All right? Multiple buffers, you can afford to do that because you have little points, little segments of the vectors, and have many flights at the same time. We also dedicate one communication thread. Out of the 24 threads of this Xeon Platinum guys, one of the threads says, you do only communication, don't let the operating system, do context switching for every thread, and that has less variability between threads. And we found out that this improves performance. So what we noticed, this is a simulation. We wrote a simulation. By the way, all the simulation and the tracing are artifacts on this paper. So we noticed that if the same thread keeps having a problem, it's always 10% slower, well, you cannot avoid having the bubble at the end. But what these queue buffers do is that they delay the onset of this bubble, exactly as it's supposed to be. But when the variability is random, every now and then somebody becomes 10% slower, and then it becomes okay again. Then you see that bubbles are completely absorbed by this scheme. So, okay, we solved the first problem. Second problem was the kind of unintuitive static scheduling. We experimented, we implemented both on one node, both static scheduling and dynamic thread scheduling. Which one is better? Now, notice a little bit here. So we decided that static is better. I'll explain why. So static means that every thread now, not process, thread, again gets a slice, a segment of the rows. It's responsible for computing the tiles inside that row, and then multiply it with this red part of the V and compute this red part of the result. Okay? And once this thread is done with its tile, it continues with the next tile. Notice that if you go downwards this way inside the thread, everybody's reusing V and just processing this in a very nice orderly manner. Notice what happens with dynamic scheduling. Yes, you may be able to absorb a little bit more of the dynamic, whatever happens in the variability, but then you destroy the cache and the SIMD-friendly way that you access all these guys. And also, It's not resident in memory for GMMs either, for the matrix vector multiplication. We're going to see how the results go with this. The next fix was to consider a tile size. What is the tile size? Microbenchmarks gave us the lead to that. We did microbenchmarks for both GMM, and you see the GMM gigaflops here, and the kernel generation, which is a different code, which is basically for loops, and that's all it does. And we saw that, of course, around 64 was best for GMM, tile size of 64 by 64 squares. This one was kind of constant, about between 64 and 256, but 64 makes more sense because you have less residence in cache. You can fit it in L1 in guess. So we used L1. And also, since this is a kernel matrix or similarity matrix, you need to difference the features between the data. Now, how many features do you have? 2, 4, 7, 10, 20? You cannot write code for each one of them, so you need a way to split the loops and then have multi-versioning compilers do the work for you. So that's what we did. We did some things by hand to get optimal performance for classical, I'd say, 2 features. But we also applied the multi-versioning on the split looping. Now, a little bit of evaluation here. The most interesting, at least counterintuitive, was the static versus dynamic. And what you see here is you see for different tile sizes, remember we said 64 is what we found as the optimal. Here's the time that it takes, and we break it down by what the 3 kernels are. Well, 2 kernels, GMM, Gaussian generation, Gaussian kernel generation, and the overhead. Now, we all agree that dynamic takes more overhead. Okay, but as you see, the overhead of the dynamic, this pink, whatever the color is, overhead, is not much bigger. I mean, it is bigger than static, but that's not why static wins, not because it reduces the overheads. It's because all this GMM becomes twice as fast. Why? Because you don't go around memory and throwing things out of cache. Everything is very nicely streamed in cache. Everything is there. You get GMM performance twice as better. Same thing for kernel generation. Okay? Now, as the tile size goes bigger, the differences subside. But you don't want to have the cache size, the tile size bigger. 64 was the optimal, so you don't want to go far. So that was interesting. The second evaluation is, remember, what did we want? We want strong scaling. We want to be able to scale up to 128, maybe to 56 nodes. And we see that for the problem sizes we're interested in, like 1 million, 2 million, or 4 million, this thing is completely scaled linearly, beautifully. Now, I want to draw your attention to the second one. The second one is the wall clock time that you see for the matrix vector multiplication with including the kernel generation. What we see is, and let me give you this thing here, which is the biggest thing where we run. It's 4 million, block size 64. So you apply a matrix size of 4 million by 4 million to a 64 vectors, and you can do it with 128 processes in less than 20 seconds. I'm sorry, less than 10 seconds. That means now your problem that people could not even run is feasible. You can run 4 million kernels, which people thought a few years ago it was impossible. In let's say 100 iterations, it's going to be less than 1,000 seconds. This is doable in this type of clusters. Also, if you care about how far you are from optimal, remember that we're doing 2 kernels. The kernel generation cannot go to the FMA peak. It can only go to the non-FMA peak of the computer. And we're doing actually much, much better than that, right? So this is pretty good. And a final piece of evaluation. I mean, it's not final. In the paper, there's more, but the final for this talk is what happens against other state-of-the-art software. So we take 2 of them. One is Cosma. Cosma is I would say it's the fastest and most comprehensive matrix multiplication software now available. And this is for parallel computing, of course, right? For distributed parallel computing. The other one is the classic scale-up pack that everybody knows and uses. And what we did is now, we could not run scale-up and Cosma to 4 million. They just work with a whole matrix. You cannot fit the matrix. These software packages do not work with that. But they can work for smaller size. So we go down and we say, what is the largest you guys, the competitors, can run? And what is the smallest that we can run? So where do we meet? Right? So we take minimum granularity for our software. What is minimum granularity? Well, you have so many threads, right? 24 threads. Let's say that every thread runs one tile only. That's the worst case you can have for our software, right? So one tile per thread for 128 or 64 MPI processes. As I said, the sizes that we pick came out to be 94,000 and 188,000. That's the smallest that we can run with one thread on 128 nodes. Cosma and Scale-up for at least the big matrix, the 188,000, cannot feed it for less than 8 processes, right? So you need at least 8 nodes to run on this. And what we see here is socket time. So we multiply how many sockets we have times the wall clock time they take. So this is the work that it's done, the energy, if you want, that you spend and you pay the power company, right? And we see that this is only for GMM, not kernel generation. We have to do apples and apples. And we see that our method is always faster. In the worst possible case, is competitive with Cosma, and that is when you only have one tile for 128 nodes. And it's many, many times faster than Scale-up. I can sometimes 17, sometimes 40, huge number, no, 17, not 40, 17 times faster than Scale-up. So we have a program that not only scales well, what we expected, but it is also very efficient, and we can use it for our kernel statistical learning computations. So what did we learn, if we learned anything here? I would say that be aware, even for symmetric multiprocessing, be aware of variabilities inside your threads, cores, if you may, right? Even 4 or 5%, which is usually, we've seen this all the time, 4 or 5% variability because of thermal issues, because of system decides to, context switch you a little bit. This can cause, wreak havoc actually to pipeline methods. So be aware of that. There is, however, ways to deal with this, preloading, reducing the variability through sometimes static scheduling, depending on what you do. And at the end, I think we have a software that makes million-scale kernel statistical learning feasible. I have one more slide. How much time do I have? 2 minutes. Well, I'll give you one more slide just for fun. And you're asking, okay, what if you don't have 5% variability? What if you have more variability? Is your static scheduling laughable? And we were really surprised. We did this with simulator. Okay, we were really surprised that actually this is the relative slowdown that I get. Dynamic gets you about close to 47, 50%, let's say, slowdown. To get the same slowdown with static scheduling, we need to increase the variability all the way to 100%. So if you spend, let's say, 5 seconds, you need another 5 seconds of variability coming in, extra stuff. So really static scheduling is not to be avoided, I would say. I will stop here. Thank you.
Okay. We have time for a quick question, if there's any questions. Yep.
Thank you for a very interesting talk. I'm Yuri Takeya from the University of Tokyo. I want to ask a question. what do you think is a potential applications or use case so you can apply your ideas to another, so you can apply to? So what's your potential use case, another use case?
So our application has been for a few years kernel read regression. The kernels are big because they can be as big as you want. Instead of running a neural network, which everybody does nowadays, you can still run statistical methods and you get some interpretability that you don't get with neural networks. The problem had been always the cubic scaling. We can take away the cubic scaling of kernel read regression with iterative methods, but the quadratic scaling of the dense matrix still remains. So this is the application. I cannot promise that I can do 1 billion where neural networks do because of the linear scaling, right? But I can promise you I can go 10 million, and with 10 million, the statistical noise is minimized.
Thank you.
Okay, let's thank the speaker again. Okay, last up on our fantastic session on matrix and linear algebra, algorithms, we have a fun talk on characterizing matrix multiplication units across general parallel patterns in scientific computing. Take it away.
Okay, thank you. Hello, everyone. I'm Yuechen Lu at China University of Petroleum, Beijing. The topic of this talk is characterizing matrix multiplication units across general parallel patterns in scientific computing. This work was co-authored with Hongwei Zeng and Professor Weifeng Liu at China University of Petroleum, Beijing, and Marc Gassas at Barcelona Supercomputing Center. And on the right is the logo of this work, QB. It's a Rubik cube. The talk includes these parts. Let's begin with background and motivation. In recent years, more and more modern processors have integrated matrix multiply accumulate units, such as NVIDIA Tensor Cores and AMD matrix cores. Compared with traditional vector units, MMU can provide 2 to 7 times higher peak throughput. This capability has already made a big impact in deep learning. However, in scientific computing, the role of MMUs is still not well understood. Well, a key reason is that scientific workloads have much more diverse parallel patterns except germ. So mapping them onto MMUs is often non-trivial. Fortunately, recent studies have indicated that MMUs can accelerate some key scientific kernels, such as Stencil, Scan, DFS. However, we still lack a systematic analysis tool that helps researchers understand how MMU works. Besides, MMU-accelerated methods for memory-bound kernels have also triggered a lot of discussion in the community. From the bandwidth perspective, kernels like SPMV and SPGEM are widely considered bandwidth bound. So if the peak bandwidth doesn't change, why can MMUs speed up them? From the compute perspective, double precision tensor core also only offer 2 times higher peak than CUDA cores. Yet many kernels use only a small part of the MMU output. Why we still see large speedups? For example, DASP SPMV can get more than 5 speedups on COP20 over cusbars. Motivated by this background as questions, it's needed to build a scientific computing benchmark suite for MMUs to systematically study their behavior. So we introduced the QB benchmark suite. It collects 10 open-sourced scientific kernels accelerated with MMUs. These kernels cover a broad range of Berkeley dwarf. For each kernel, QB includes one MMU accelerated method with a vector unit-based baseline. At the same time, we also find that among these algorithms, most of them make a large adjustment to their data format and computation data flow, workflow in order to adapt to the computation patterns of MMUs. So we get our first K observation. To exploit MMUs, non-drum algorithms in scientific computing often have to modify data structures and reorganize algorithms. To better understand how 10 workloads use MMUs, we introduced a categorization scheme. It has 2 dimensions, input utilization and output utilization. And each dimension has 2 levels, full and partial utilization. Then we get 4 quadrants. In quadrant 1, kernels have full input and full output utilization, which is very close to a standard dense MMU usage. Quadrant 2 includes scan. It uses partial input but still produces full output. Quadrant 3 includes reduction. It's partial on both input and output. For scan and reduction, they both use a constant matrix. For quadrant 4, kernels use full input but only a partial output, including BFS, GEMV, SPMV, and SPGEM. Then we get the second K observation. Scientific kernels may not fully utilize the dense input and output matrix of MMUs, exhibiting distinct utilization patterns in 4 quadrants characterized by varying levels of density. Then is the evaluation part. We evaluate QB on 3 NVIDIA GPUs, and each workload is evaluated using 5 test cases. To understand where performance gains actually come from, we considered 3 implementation variants. The first one is Tensor Core version. We call it TC. This version uses Tensor Core for computation and calling FP64 MMA instruction to compute the tail level jump. Take the GEMV as an example. In TC version, Tensor Cores comply a dense tail with a tail that formed by scaling the input vector x. As a result, only the diagonal elements in the output tail are the real results. The second one is a CUDA core MMA replacement. We call it CC version. It keeps the same data structure and algorithms as TC, but replace MMA with CUDA core computation. In GEMV, the CC version using CUDA cores to compute exactly the same work as the TC version. The last one is CUDA core essential replacement. It computes only the essential parts on CUDA cores. It removed the extra work introduced by MMU mapping. Then we evaluate the performance of baseline, TC, CC, and the CCE for all workloads on the 3 GPUs. there is a lot of data in this figure, so it's a little bit hard to extract the key point. To make the trends clear, we further summarize the results using speedups shown in these 3 plots. We analyze this speedup plots by asking 3 questions. The first one is, do MMU accelerated kernels outperform vector-based implementations? To answer this question, we compared TC version versus baseline and got the performance plots. For Q1, quadrant 1, the kernels in this quadrant, their MME input and output tails are well utilized. So TC show portable speedups across architectures. For Q2 and 3, these kernels using constant matrix as operands reduce data movement. So it's leading to better performance. For quadrant 4, with higher memory bandwidth on H200 and B200, TC shows a clear advantage over the baseline. This leads to the third key observation. MMU accelerated workloads consistently outperform vector baselines in most cases and exhibit performance portability across the Ampere, Hopper, and Blackwell architectures. The second question is, with the same data structure and algorithms, how much speedup come pure from MMU hardware? So we compared CC versus the TC version and got this performance. For Q1, the tendency of these kernels is consistent with peak throughput gaps. That CC is 2 times slower than TC. And for Q2 and Q3, the kernel's tendency is beyond peak throughput. CUDA cores cannot exploit. We guess that CUDA core cannot exploit constant matrix as effectively as tensor cores. For Q4, we can see that the gap is smaller, but TC still wins. TC can benefit. We can see that TC can benefit bandwidth-bound kernels. This leads to the key observation 4. Removing the impact of data structure and the algorithm, MMUs account for 10% to 200% of the performance gains. The third question is a redundant work introduced for MMU mapping worth it? Would vector units can be faster after removing it? To answer this question, we compared the CCE versus the TC version and got this performance. For Q2 and 3, the TC is still faster overall, so the redundancy is generally worthwhile. For Q4, for most kernels, CCE is close to TC. Since TC also beats baseline and the CC version, the introduced redundancy is usually justified. But for SPMV, after removing redundancy, the CCE can be further improved. So we get the key observation 5. Generally, the redundant computations introduced to enable MMU-friendly matrix computing patterns should not be removed. The only exception is SPMV, where avoiding the redundancy yields up to 20% higher performance. In addition to performance, we also measure power, energy, and EDP for each workload on H200. we can see that in many cases that the instant power of TC can be similar to CC version. But TC can finish faster, so energy and EDP are lower overall. The key observation 6 is that MMUs exhibit similar power consumption to vector units, but complete computation significantly faster, resulting in 30% to 80% lower geomean EDP across all workloads. For the numerical accuracy part, we measure double precision numerical errors on H200 and B200 using we use the serial CPU results as the reference. We can find that the TC and the CC version show identical average and maximum errors. However, the errors can vary from baseline to TC and CC, sometimes by more than one order of magnitude. This leads to key observation 7. MMUs and vector units provide comparable numerical accuracy, but algorithmic transformation for MMU utilization can introduce significant numerical deviations that undermine the reproducibility of scientific results. To better explain the performance trends we just saw, we use a catch-aware roofline model. These plots show performance versus arithmetic intensity with rooflines for both compute and memory limits on H200. In Q1, without advanced germ optimization, TC germ does not reach peak throughput. In Q2 and 3, reduction and scan use segment processing and are cache-friendly, so TC can even exceed the DRAM bandwidth roofline. In Q4, TC, CC, and CCE change memory access patterns and get closer to the bandwidth roofline than the baseline. So we get the key observation 8. Adapting data layouts and algorithms for MMUs fundamentally alerts memory access patterns, often yielding more regular access and significant performance gains. The next part is comparison with other benchmark suits. We compare QB with two widely used GPU benchmark suits, Rodinia and Shock. QB covers more Berkeley-Dorf and offers broader characterization. And we further validate diversity using hardware profiling. We collect the following NCU metrics and run PCA. QB workloads show a wider spread in the principal component space. Then we get key observation 9. Originally developed with the primary goal of evaluating MMUs, the QB benchmark suits encompasses a wide range of behaviors in scientific programs, positioning it as an effective tool for assessing modern processors. The final part, conclusion. We present QB, a benchmark suite of MMU-optimized scientific kernels. QB covers diverse parallel patterns at kernel behaviors and evaluates performance, power, and numerical accuracy, providing practical insights for architecture, algorithm, and application researchers. This is a call for preserving double precision MMU capability. Because we found that the double precision tensor core capability drops on B200. And our results demonstrate that FP64 MMU acceleration can benefit most scientific workloads. So given our observations, future GPUs should keep double precision MMUs as a core capability. That's all. Thank you.
Okay, thank you for your talk. So, just something I want to make sure is that what's the precision you use in this study?
Double precision, only double precision.
So it's double precision, and then in the last slide you also showed that tensor cores double precision is the same as CUDA core. Can you explain more why you still see speed up in Blackwell while using tensor core over CUDA core?
Blackwell, we used tensor core.
Yeah. I think in your results there's still lots of place you can see that Blackwell's because Blackwell tensor core and CUDA core has the same performance in theory,
yes,
right?
Yes.
And then in your plot, we still see speed up while using tensor core. That's something I'm a little not understand why.
Yeah, we found this very strange thing, performance, and we guess that it can be benefit when we use tensor cores. It can be benefit by some, I guess maybe some instruct or pipeline design. I'm not sure. All of these things designed for tensor cores maybe also helps this performance gains.
So what specific design you use for tensor core that is not used in CUDA core in your current benchmark shows?
Sorry, could you?
So you say there's some hardware design that might beneficial for using tensor core.
Mm-hmm.
Then it's like the following question is which specific feature you are using that's using in tensor core, not using CUDA core right now?
Absolutely, the compute power.
But again, it's like in your last slide, you already showed that tensor cores
yes,
performance are same as CUDA.
Yes. I guess maybe we need to do more profiling to know how it works, because it's a little bit hard to know how the architecture design and so on.
Okay, yeah, but I personally feel very desperate about it. It's like the vendors preserving the double precision tensor core. Actually, if you see the Rubin's roadmap, they no longer provide double precision tensor core.
Yes, so we provide.
Yeah.
We want to.
And this is an open question. If that being the case, is like in the future we no longer have double precision tensor core.
Mm-hmm.
What do you think this benchmark should be evolved to?
I think the next generation only. That's only the NVIDIA's design, right? Plan, right?
Here's the thing: it's like if you look at the hardware design, double precision usually take much more space than using the lower precision tensor core. That's the reason why the vendor not really want to have double precision tensor core.
Yes, but the scientific computing is also very important for everyone, and I think we need more people to highlight the importance of scientific computing.
Okay, thank you very much.
Thank you. Thanks. Let's thank the speaker again.
Thank you.
We now have a break. I apologize for those who had extra questions, but fortunately, one can presumably be able to find the speaker at the break.
And I will just also include PPoPP. I thank you all for being here. Thank you for traveling to Australia to attend. It's been, I think, a very, very successful conference, and I'm pleased to see the last holdouts here in the room enjoying this last session. But thank you all for coming to PPoPP this year. Thank you.